Welcome to Civil Engineering Masters. Today we are going to discuss regarding the design of beams. Okay, this design will be as per IS 800 2007, which gives the different conditions for the design of building depending on limit state method. Okay, first of all we will see what is the beam. Here if you see there, a structural member which is subjected to transfer loads is called as a beam, okay, which can carry all the vertical loads which are acting over the beam, and these loads will be perpendicular to the longitudinal axis. The applied load which are there over the beam, those all are perpendicular to the longitudinal axis. Those we used to call as the beams. Okay. When we used to provide these beams in buildings, these beams we used to provide to support the roofs. Okay, the beams which are supporting roofs we used to call as the joists. Okay, and these joists all are, you can see here, a large beam supporting a number of joists is called as the girder. These all joists will be supported over the girder member. Okay, and exterior beams, these beams are having the various names you can see here, and the exterior beams at the floor level of buildings which carry part of the floor loads and that of the exterior wall, part of the floor loads as well as exterior wall are called as the spandrels. Okay, the beams you can see here, exterior beams at the floor level of the building which can carry both the loads. You can see here floor loads as well as exterior wall load, the load due to the wall. That one, those type of beams we used to call as the spandrels. Okay, beams which carry the roof loads in trusses we used to call as the purlins, and those which supports the load from the masonry over the opening are called lintels. Okay. Here two things we can see: beams which are carrying roof loads in trusses they used to call purlins, and those which supports the loads from masonry over the openings. The masonry which we used to provide over the openings like windows or doors. Okay, the masonry or the brick wall which is there, or any type of wall, masonry wall which is there over that particular opening, the beam which carries this load are called as the lintels. Okay, and a horizontal beam spanning the wall columns, a horizontal beam spanning the wall columns of industrial buildings used to support wall covering is called as the grill. If you support any covering material over the beam, okay, in front of above the near to the openings of the shed, any industrial buildings, those type of beams we used to call as the grills. Okay, these are the various type of beams which we used to use in steel structures. And here I am going to explain regarding some of the important things which are required while designing the beams. And here in these diagrams you can see some of the beams. You can see here girder beams which are provided over the bridge piers to support the slabs, or any slab which we used to provide over this particular bridge. Okay, for those bridges, those slabs will be supported by this different type of girders. Okay, this type of girders, these also we used to call as the beams. And here we can see the rafter is a one type. If we can see here, rafter and purlin. Okay, purlin which is nothing but a type of beam which can carry the roof material which we used to provide to cover the openings. Okay, here we can see these are the cover materials. Okay, roofing materials. We used to cover these all materials over this particular purlin. This purlin has to carry all this covering material, covering roof load, as well as some of the nuts and bolts fixtures which we used to provide fix this particular purlin with the covering material. And some of the beams and columns in construction we can see here we can see some of the columns are there. And if you see here, floor beams, which we used to call as the joists, and these are having the lesser dimensions. You can, when you comparing it other beams, these beams will have the very less depth. Okay. And the floor girders, and this, if you see these joists are supported by this particular one of the beam. You can see this beam is having the somewhat higher depth. Okay, this higher depth of this particular beams we used to call as the floor girders, and these floor girders they used to support different type of joists. Okay, and also we can see here some spandrels which are provided external side of the wall. And these walls they used to support the covering materials, covering walls. These spandrels they carries floor loads as well as we can say wall loads, the loads which are supported over these beams. Those loads also carried by these spandrel beams. Okay, we used to provide exterior side of the exterior side of the structure. And some of the floor slabs will be there, and some of the floor beams we can see here. And different type of beams we used to design in steel structures depending on their requirements. Okay, some of the concepts which we used to use design a steel beam in as per limit state design. You can see here section force deformations responses. We can see here we used to consider section force deformation responses we used to take, and plastic movements which the particular beam will carry. Most of the beams they used to carry movements. Okay, trusses will carry axial forces. Similarly, beams they used to carry moments and shear forces. Okay, here while we design these particular beams, we used to go for the plastic moment, maximum moment that the structure which can, that the beam which can carry. Okay, and a beam is a structural member that is subjected to primarily to transfer loads and negligible axial loads. Axial loads will be there, but they are very negligible. Okay, and this, because of this transfer loads, there will be a generation of shear forces will be there along with the bending moment. Okay, flexural, these beams will be flexural members actually. Along with the flexure, there will be a force of shear. There also a shear force which is generated inside the beam member. And the internal shear forces and bending moments causes longitudinal axial stresses and shear stresses in the cross section. If you see here, you can see some of the longitudinal axial stresses. These we used to call as the longitudinal axial stresses. If you see one here at the top of the neutral axis, if you take here in this curve x-axis, you can see movement along the x-axis. About the x-axis, if you see there you can see the forces, compressive forces. You can see above the neutral axis, and below that particular axis we can see the axial tensile forces. Okay, and this particular graph will be indicates the stress strain curve for this particular selected beam, the beam which is having dimensions depth d and width b. It will carry the load, bending moment as well as shear force. These two are the internal resistance which are offered by the these are the shear, bending moment and shear force which are comes from the applied loads over the beam. Okay, if you see stress strain diagram, here strain will be linear in both the cases. Stress also in this case we have taken linear. Okay, but in this case, in case of this one, we can see force diagram, stress diagram for this particular material. Here we can see this one, and here top portion will carry axial compressive forces and bottom portion of the body will be carries tensile forces. For beams, we used to use curvature relationship. Okay, pi is equal to 2 epsilon by d, which is given by the equation for pi. Okay, and F here we can see the shear force, which can be varies with respect to the load. Okay, and here we have calculated the shear force along the cross section also, along the about the cross sectional width. We can find sigma of minus d by 22 plus d by 22. This shear force will be force will be acts varies along the cross section. Okay, force will be same, but stress, when we calculate the stresses, then we used to take depth dimensional parameters of the body. And similarly we can see the movement, bending movement, which can be comes from the load. Okay, sorry, this is from the section, which is resisted by the section. Okay, and some of the assumptions we used to assume plane sections remains plane will be valid for this type of sections. And as we know, stress diagram of the mild steel, up to elastic limit, stress is directly proportional to strain as per Hooke's law, and it obey the Hooke's law. And after that, it will reaches its maximum limit with highest amount of ductility. You can see the highest amount of deformation, as you can say in terms of strain. You can see maximum strain, which is obtained at the maximum stress, ultimate stress. Okay, this stress, if you see here, maximum stress has been obtained at longer, at the very higher variation of the deformation. Strain, there is a very huge amount of variation will be there in case of strain. Okay, in ultimate condition, larger amount of deformations we can observe in case of strain diagram, in case of strain, but load will be near to applied sigma y. But in case of ultimate load, in case of ultimate strain, we can see the maximum deformation of the material. Depending on this one, okay, we used to classify this particular stress strain curve by using bilinearization method. We used to make it line first up to elastic limit, it will be linear. After that, it will be non-linear, means it will be straight line. If you take like this, you can take this type of curve. In this particular diagram, if you can see here, this one is the plastic movement. Okay, there will be two type of movements will be there: yielding movement, another one is the plastic movement. Whereas the yielding movement we used to indicate with the letter my, and plastic movement we used to indicate with the notation mp. Okay, the steel stress strain curve is approximated as a bilinear elastoplastic curve with yield stress is equal to sigma y. Then the sectional moment curvature m pi response for monotonically increasing moment is given in this particular figure. Okay, here in this figure, this moment curvature relationship has been given in this particular diagram. Up to the elastic limit, we used to apply the maximum load. Also, we used to take up to yield movement. At this, up to this point, the load will be up to yield limit. Okay, it not after the means it will be elastic limit. After this, there will be some of the yielding will be there. Okay, up to elastic limit, stress is directly proportional to strain. Okay, both are linear only. We can observe here both the variations will be linear. At the point A, stress at the compression zone will be proportional to strain. Okay, these both are linear. In case of B, there will be some variation has been came. Okay, it there you can see at this stress diagram, there will be bilinearization has been started in case of stress diagram. Okay, but strain is linear itself. You can see up to 2 epsilon y also strain will be linear, but in case of stress, you can see linear and plastic type of variation. Stress, you can see bilinear stress condition here. Okay, when you keep on increase the moment over that particular structure up to 5 epsilon y, if you take for example at the point C, this is the maximum moment or maximum ultimate load in case of stress load and deformation condition. If you take, this is the maximum load in case of stress strain diagram. If you take of mild steel, if you take, this is the maximum ultimate stress which we used to take. In case of moment, if you assume it as moment, it is the maximum moment which the structure can be taken. That maximum moment we used to call as the plastic moment. Why? Because there will be, we can observe after this particular point, say yielding will be yielding will be, sorry, elasticity will be losses here at this particular point. Okay, and after this point yielding will be stops at this particular point. And what happened here after C, the deformation, the yielding deformation, it will be keeps on increase without increase of any movement. Okay, here you can see that this curvature has been increased from C to D, D to E, up to E. Okay, after E, it is the maximum load or maximum movement, sorry, maximum strain which can taken at the maximum movement. Okay, the maximum strain of the structure which can resist when you apply the constant movement after C. Okay, movement plus this maximum movement we used to call as the plastic movement. Okay, this plastic movement, when it will be reaches, you can see the diagrams for C, D, we can see sigma y will be there, whereas the linear, this particular linear curve will be slowly reduces its length. Okay, and when you reaches to the A, there won't be this particular linear that elastic limit will be diminishes. Okay, there won't be any elastic limit, the structure is going to break. Okay, it will be these plastic sections mostly fail suddenly. Okay, there will be sudden failure, it will be there at the end of the point A. Okay, if you see this diagram, this particular stress strain curve has been correlated with this beam type of condition. If you see here. Okay, when you apply the moment up to yield point, there won't be any variations, there won't be any stresses you can see in this one. It will be the change of this particular beam will be, length will be within the yield limit itself. When you keep on increase that load at point 2 also, there will be some balancing moment will be there. Okay, there won't be any difference. The structure it won't regain its original it will regain its original shape and size. You can see the point sigma y itself, it will regain its original shape and size. But in case 3, you can see small deformations has been started after yield limit. Okay, after when it has been reached crossed this yield limit, we can slowly see the deformations of this particular beam. You can see here necking portion of this particular beam, you can observe here when you apply the flexural load. Here dimensions has been changed, thickness of this particular material has been changed. Okay, at D, if you see, this is the maximum point, the maximum load, this is the maximum load which can be taken by the material. Not only the D, if you keep on increase the load, at E we can see this type of raw before going to fail. Okay, up to the point E, it will be takes somewhat load. Okay, not somewhat load, the constant load. Okay, MP, maximum plastic moment at constant moment, it will goes on increase its length, or sorry, it keeps on increases its curvature. Okay, the length of the curvature has been has increased in this at up to this particular point A. Okay, after this point, this section is going to fail. Okay, this process we used to call as the plastification of the cross section. Totally this section is going to fail, the section is going to break at this particular point. Okay, this breaking of this particular beam section we used to call as the mechanism. Okay, that failure of those structures we used to call as the mechanism. Okay, as shown in figure, My is the moment corresponding to the first yield and MP is the plastic moment capacity of the cross section, the maximum moment capacity of the cross section. Okay, the ratio of these two, plastic moment to the yield moment, is called as the shape factor. And one more thing, plastic moment will be always more than the yield moment in all cases. Okay, and this shape factor we used to calculate by using their ratios. Okay, whereas the shape factor S is equal to MP by My. Okay, for rectangular cross sections, the shape factor is we used to take as 1.5. For wide fanged sections or any I sections, we used to take shape factor as 1.1. Okay, calculation of the MP, for the calculation of plastic movement, we used to take the cross section which is subjected to the maximum stress as well as maximum tensile stress and maximum compression stress. Okay, up to their limits we used to take. Okay, the section is going to fail in compression or the section is going to fail in tension. Both the conditions we used to take. The maximum compressive stress we used to take as sigma y and maximum tensile stress we used to take as minus sigma y. Okay, at the plastic limit. Okay, at the plastic limit is nothing but maximum strain point which is going to fail. Okay, maximum strain point, the point E, maximum yield after before the breaking. Okay, that one we used to take as the plastic moment, the moment which is corresponding to that particular deformation we used to take as the plastic moment. Okay, this is regarding plastic moment. And when section is fully plastic section, okay, in fully plastic section you can't see any linearization of these particular portions. Up to D point you can see the sum of the bilinear curves, but in case of complete plastic section, fully plastic section, you can't see any linear sections. If you see in this diagram, here you can see that you can observe the linear stress and non-linear stress. Okay, constant stress diagram. But in case of fully plastic sections, we can't see any linear curves. We can see the completely plastic section. See here, it will shows as the rectangular section. It looks like rectangular section. Okay, in this fully plastic section, you can see the fully plastic movement of the section. Okay, if you take any section, just assume here the plastic movement capacity of any section may be computed with reference to the movement curvature relationship. Okay, here we know the movement curvature relationship. What we know, My is equal to Fi into Za. From the movement curvature relationship we can derive this one. Okay, by using the flexural equation, M by I is equal to F by Y is equal to E by R. By using that flexural equation we can derive the moment curvature relationship. From there we can see here My is equal to yield stress, My is equal to Fi into Z. This is regarding the maximum yield stress. Okay, this yield stress you can see here, consider a fully yielded beam section. The bending stress distribution will be rectangular as shown in the figure. Okay, if you take this fully yielded beam section, if you take this diagram, in this diagram what they have given, the bending stress distribution will be rectangular. You can see here rectangular shape of the bending stress distribution. Okay, here bottom portion of the section and top portion of the section, you can see the rectangular type of section. Formation of this particular section will be in rectangular shape. Okay, and let the nature of the bending moment be sagging such that the fibers above the neutral axis are in compression and those below the neutral axis are in tension. If you take this one as the beam section, or if you take this one as the beam section which is taking bending moment, and that bending moment also in sagging in nature. Okay, if you take that sagging moment, the above the upper part of the neutral axis we used to take as the compression zone, and bottom portion of that particular beam we used to take as the section we used to take as the tension zone. Okay, this particular section, depending on these conditions, we used to find the neutral axes of the section. Okay, here in these plastic sections we used to classify the sections depending on their moment curvature equations. Okay, their plastic moment equation. Okay, if you take this plastic moment section, the section which is changing its nature from tension to compression, that that changing portion we used to take as the equal area axis. Here we are not using the neutral axis, here we are using the equal area axis. Okay, the area of the bottom portion will be equal to the area of the top portion. Equal area axis which is indicates the stress which is comes at the top will be same as the stress which is generated by the bottom section, or the forces which are generated at the top will be equal to the stresses which are generated at the bottom, and which means that exactly the compression stress C is equal to the yield stress of that particular material into area of cross section of upper part of the portion. Okay, the above part, the portion which is above the equal area axis. Similarly, force in tension T is equal to Fi into A2, area of the bottom section, bottom portion of the section. Okay, by using this fully plastic movement diagram, we used to find equal area axis. By using this equal area axis, we used to divide this section into two parts as A1 and A2, which are having the centroidal distance of these two sections will be Y1 bar and Y2 bar. And depending on this A1 and A2, we used to find compressive force as well as tensile forces. Okay. Okay. After taking those forces from these sections, we used to take equilibrium equations. Some of the we used to take equilibrium equation that moment about the axis will be zero. Okay. Or we used to balance the forces. Forces taken by compression material is equal to the forces taken by the tension zone material. Okay, C is equal to compressive force is equal to the tensile force, whereas C indicates the upper part of this particular body, Fi into A1, and T is nothing but bottom portion of the body, Fi into A2. Here we used to take yield stresses. We are assuming that yield stress is the maximum stress in this case. Okay, and A1 and A2 are the equal areas. If Fi will be get cancelled in both the cases, A1 is equal to A2. Okay, for this particular A1, the area of A1 we don't know exactly here, and A2 also we don't know. When A1 will becomes to the A2, what it indicates, the area of the both the sections will be same. What this indicates, A1 is equal to A2 indicates the area of this both this complete section will be, this both the parts will be equal. Okay, when this both the parts will becomes equal, when we consider half of the areas of the bottom portion and half of the bottom portion of area of the upper portion are equal, then only this condition will be satisfied. Okay, whereas A1 is the area of the section above the neutral axis. Actually it is not neutral axis, it is the equal area axis. Okay, and A2 is the area of the section below the equal area axis, and A is the area of the cross section of the beam. Okay, therefore the neutral axis of the plastified section is sometimes called as the equal area axis. Okay, this is regarding the equal area axis. By using this one, we can find the maximum plastic moment of the section. How we can find that maximum plastic moment? The forces we know two forces are there. Okay, what are those? Tensile force as well as compressive force. These two forces, they are generating couple inside the beam. Okay, because of this nature, beam will be generate couple inside the beam. Okay, from the couple which resists the plastic movement, we used to find like this. moment of plastic movement is equal the moment generated because of these two opposite nature forces will be mp. That one is maximum sorry, that is plastic movement, which is nothing but Fy into A1 into Y1 bar. You can take here where area into lever arm and same as area into lever arm. If you want to find moment in the body, okay, for that what we used to take force from the central or neutral axis or equal area axis, the distance of the upper portion, centroid of the upper portion area into force generated at that particular distance. Okay, force which is nothing but in the upper case Fy into A1 into centroidal distance will be Y1 bar for the upper portion plus Fy into A2 which is nothing but force into Y2 bar is nothing but centroidal distance of the bottom portion of the section, tensile part of the section. This two will gives the maximum plastic moment which is taken by that particular beam. And in case of this one, in place of A1 and A2, we are going to use A by 2, whereas A1 is equal to A2 is equal to A by 2. I am going to use that one. And if you substitute those A1 and A2 values here, you can get the equations like this, whereas maximum plastic moment will be maximum moment will be mp is equal to Fy, it will be remain same, A by 2 into Y1 bar plus Y2 bar. Okay, and this one is called as the maximum, this one is called as the plastic moment of the section. And this plastic moment, if you represent this one A by 2 into Y1 bar plus Y2 bar, this will indicate the plastic modulus of the section Zp. Okay, this particular portion A by 2 into Y1 bar plus Y2 bar, this will indicate the plastic modulus of the section. Okay, and final equation we can get like this: mp is equal to yield stress will be remain same, and this section plastic modulus of the section will be A by 2 into Y1 plus Y2 bar will be indicated as Zp. And here Zp you can see mp is equal to Fy into Zp. This one is the maximum plastic movement. Okay, and Zp will be the plastic modulus of the section, which can be indicated by A by 2 into Y1 bar plus Y2 bar. Whereas Y1 bar and Y2 bar are the distance of the gravity of the area above and below the neutral axis respectively. Okay. This is regarding the plastic moment of the section and sectional modulus, plastic modulus of the section. Okay, and this classification of the section depending on their nature, depending on stress strain moment rotation diagram or moment curvature diagrams, we used to divide these sections into the 4 classes. Okay, how we can define? One, the section which is completely plastified, completely gone under the rotation, maximum rotation of the section has been obtained. Okay, by using bilinearization curve here, if you see here, the maximum rotation has been obtained at the maximum moment, and that maximum moment will be indicated with the plastic moment. Okay, maximum plastic moment for this type of section, this section will be obvious completely yielded portion. We can see complete section has been yielded, it is going to fail at that particular point. Okay, this type of sections we used to call as the plastic section. There won't be any elastic nature in the material. We can see the plastic nature of the material. Those type of section we used to call as the plastic sections or class 1. Okay, some of the sections which are within the middle of the section, it won't obey the complete rotation, it won't gain complete yielding. Okay, the section is not going to rotate completely, it will be going to complete before the plastic section. Okay, that portion we used to call as the, that behavior we used to call as the compact section, compact class 2 of the material. Those sections we used to call as the compact sections. Similarly, semi-compact sections, we can see some of the portion of the section will be linear and some part of the portion of the section will be non-linear. Okay, it will be up to maximum yield point. Okay, this up to maximum yield point, the section we used to call as the semi-compact section. For slender columns, they undergoes very large amount of deflections. That's why we used to call as the slender sections. Okay, slender sections, the class 4 we used to see here. The most of the sections will be under the elastic limit itself. Okay, here in this diagram we can see the movement rotation behavior of the four classes of the cross sections. You can see here for plastic section, MD plastic design moment will be ZP into Fy, and compact section also we used to do same thing. For semi-compact section we used to take here ZE into Fy, and for the slender section also which we used to take MD is equal to ZE effective elastic section modulus into Fy. Okay. These are the different classifications of the sections in beams which we used to use. And regarding those plastic sections, we have given here, you can see plastic section or class 1 section, cross section which can be developed plastic hinges and have the rotation capacity required for failure of the structure by formation of the plastic mechanism are called as the plastic sections. Okay, what they are telling here, the section is going to fail. The section, if you take any beam, the beam is going to break any 2 points. Okay, any 2 locations of the beam. Okay, the failure of those at those particular 2 joints in case of fixed support conditions, if beam fails any 2 locations in that particular beam, okay, means if it breaks any 2 locations, the section is not going to take any movement at those locations. And if you keep any body also, the section won't be withstanding. Okay, it will keeps on moves in downward direction or upward load applied direction. It keeps on moves in the it will break at particular point. Okay, those type of section we used to call as the plastic sections. Okay, compact sections, cross section which can develop plastic moment of resistance. Okay, but have inadequate plastic hinge rotations capacity for the formation of plastic mechanism before buckling are classed as the compact section. Okay, here what happened, there will be plastic hinges will be there. Okay, when we provide the hinges in between the beams, the section is going to rotate about that particular hinge. If you break at any if any section undergoes deformation at that particular at any particular location, at that location the beam will be moves in to and fro direction. Okay, the beam is going to deflect at that particular point. Okay, but it won't fail, it won't break, but there will be chances of yielding is there in that material, but the material is not going to fail. Okay, to fail that one, it has to require another extra hinge. Okay, with if you take any fixed support condition with single hinge with single breaking point, okay, single yielding point, the structure is not going to fail. Okay, when it is going to fail, if it forms additional hinge, then structure is going to fail. Okay, the hinge rotation capacity, okay, to fail that section, to collapse that particular fixed beam, it required minimum 2 plastic hinges. Okay, then only it can fail. Okay, if it is having the insufficient hinges, then the section is not going to fail. Okay, we can see here have inadequate plastic hinge rotation capacity for the formation of plastic mechanism before buckling are classed as a compact section. This type of sections we used to call as the compact section. Semi-compact sections, cross section in which the extreme fiber in compression can be reaches yield stress. Okay, assuming an elastic distribution of the stress, but cannot develop any plastic movement of resistance due to the local buckling are called as the semi-compact section. It won't develop any plastic movement in these sections. This type of sections we used to call as the semi-compact sections. Okay, next one is slender sections, class 4 sections. Okay, cross section in which the element buckles locally even before attainment of yield stress are called as the slender section. These sections will be buckles before it is reaching to the yield stress. Okay, it will deforms in horizontal direction. If sorry, in case of beams, those will be deflect in vertical direction. Okay, those type of deflections failure before reaching the yield limit, sorry, elastic limit. Those type of sections we used to call as the slender sections or class 4 sections. Okay, these are the various type of sections which we used to assume in the design of beam sections. Okay, here we can see different type of sections which we can use as the beam sections. Okay, for rolled beams columns we can use beam and column section for columns as well as beams. Sometimes columns also subjected to horizontal forces like wind forces. In those conditions also we used to design as a beam. By considering as a beam we used to design. Okay, we can see here notations of the beams: D, B, and thickness of the flange, width of the flange, B, small b. Okay, we can see different parameters here. Okay, which correlated with the classes of the section. Okay. Similarly for channel sections, rectangular tubular sections, circular hollow sections, we can see different sections having different cross sections. You can see here different sections having different cross sections. Okay, we can see here rolled middle sections, angle sections, T sections, or double angle sections. We can see here by using these all sections we can make a flexural member or beam member. We can see some of the built-up beams also here at the bottom line. Okay, these are the various type of sections which we can use for the design of the beam sections. Okay, these all are regarding the sections of the beams. Now we can see the here you can see limiting width to thickness ratios. Okay, depending on their selected section, we used to take their width to thickness ratios to decide the section. Section belongs to the class. Okay, if you take any section from the roll mill, okay, outstanding element of the compression flange. Okay, any compression flange, top portion of the section. If you take I section, in that case top portion of the I section. Rolled sections, if you take roll mill sections, then B by thickness of the flange width ratio is 9.4 epsilon. Then we used to consider the selected section as the plastic section. If it is from the 9.4 to 10.5 epsilon, then we used to assume that section is the compact section. If it is more than this one, we used to assume semi-compact section. If it is more than, then those sections called as the slender sections. Okay, we used to classify these sections like this: three different sections. Class of the plastic, whether it is plastic section or it is compact section or it is semi-compact sections. Depending on these three conditions, we used to classify these classes, compact sections. Okay, here we used to assume width of the section. If you see B value here for I section, we used to take B is this one, and thickness of the flange TF. By these two ratios, if these two ratios are less than 9.4 epsilon or equal to 9.4 epsilon, then we used to assume the section is the plastic section. Similarly for the compact section, if it is more than 9.4 and less than 10.5 epsilon, then we used to take section is the compact section. Similarly for semi-compact sections, we can see here if it is 15.7 epsilon, the section is the semi-compact section. We used to use formulas belonging to semi-compact section. For these three conditions, movement equations will be different. Design movement will be different for these three type of sections. That's why we used to classify all these three sections depending on width to the thickness of the flange ratio. Okay, and welded sections we can see here bottom. These are the ranges. For similarly internal elements of compression flanges, internal elements of compression member. Well, this type of sections, for this type of element of compression flanges. Compression due to bending. If you observe any bending of the flange section, in those cases what we have to do, B by TF should be less than 29.3 times to the epsilon. Similarly for the compact section and for both the cases semi-compact section. And axial compression cases, there won't be any applications of plastic sections and compact section. But if you are assuming semi-compact section, if the ratio, if you got 42 epsilon, then the section is going to will be decided as the semi-compact section. For web of an I, H or box sections, generally we used to consider these are the different formulas. If the I sections having neutral axis at mid depth, if the neutral axis and equal axis, if both are matches, then we used to take d by thickness of the web section, and we used to classify the sections like this: 84 epsilon, 105 epsilon, 126 epsilon. These are the three ranges which we used to design a beam section. Similarly for angle sections, we can see at bottom, okay, angle compression due to bending. These sections we can see here. For different cases we can see here different type of limits. For channel section, web of the channels also they have given here d by thickness of the web ratio. This one also we can use for the design of beam sections. Okay, these all are the remaining properties of the sections, whereas the epsilon indicates the under root of 250 by Fy. Okay, here d is the depth of the web, we can see here. Okay, after that we can see here some of the failures which happens inside the beam. When we apply the flexural loads over the beams, we can see some buckling failures in the beams. Okay, if you see a beam which is fixed in between the tested mission, okay, in this testing mission they have applied flexural loads over this beam, and these beams got deflected. Okay, the smaller portion of this beam got deflected. This type of deflections or this type of buckling of the beam we used to call as the web crippling. Okay, this portion, smaller portion, bottom portion of the beam has been buckled. Okay, this type of buckling we used to call as the web crippling. If you see in the second diagram, here in this diagram, second green diagram, web crippling has been observed in this particular beam. Similarly, web buckling, when the total flange of the beam deflects a side, okay, it is moves away from its original neutral axis, so vertical axis, then the buckling of the beam we used to call as the overall buckling or web buckling of the beam. Okay, these are the failures which we used to observe in case of beams. These are the failures which occur in the beams. Okay, for that we have to check buckling failures of the beam also, and we used to check deflection failures of the beams also. Maximum limit of the deflections also we used to consider, and sometimes these beams may be fail in the flange section also. This failure are called as the local buckling or crippling of the beam. Okay, and while designing the beams we used to know where the beam is laterally supported or unsupported. Okay, what is the difference between laterally supported beams and laterally unsupported beams? Here we can see two type of beams: laterally supported beams as well as laterally unsupported beams. Okay, first of all we will see laterally supported beams. Okay, here we will see laterally unsupported beam. Okay, beam with major axis bending and compression flange not restrained against lateral bending, okay, or inadequate lateral supports, and it will be failed by lateral torsional buckling before attaining their bending strength is called as the laterally unsupported beam. For suppose if you apply any load over this particular beam, okay, if you apply, okay, if you see in this diagram, if you apply any load in this direction vertically to this particular beam, if you apply vertical load to this beam, okay, sometimes what happens because of eccentricity or because of overload, this beam will be get rotated, okay, this beam will be rotated in torsional direction about the ZZ axis. This beam will be going to rotate. If you see from this diagram, second diagram, okay, original axis of this beam will be like this, okay. Initially it will be vertical, this position will be here, this beam will be situated here, but after application of the load, this particular beam has been rotated in this direction, and it has deflected. The top portion of this beam has been, this compression portion of this beam has been deflected away from the its vertical axis, okay. This type of deflections we used to call as the lateral deflections of the beams, and this type of supports we used to call as laterally unsupported beam. There is no provisions we have provided to restrict these deflections. We are not going to resist deflections for this beam. There is no material or no support has been provided to overcome this rotational deflection, torsional deflection, okay. This type of beams we used to call as the laterally unsupported beams, okay. This is one. When you restrain this particular deflection rotation, okay, when you restrain this rotation or twisting, okay, and when you restrict this deflection, lateral deflection of the beam by providing some struts and as well struts, and by providing slabs or lateral bracings, okay, by providing some bracings, you can restrain this deflection, okay, by supporting this at these particular locations, by supporting here and here, or by covering them by providing material over this particular flange part, you can restrain the beams, okay. You can control the deflections. This, when you provide any support to this particular flange portions, those portions are those type of beams we used to call as the laterally supported beams. If you see here, here you can see top portion of the this particular I section has been inserted inside the slab, this casted inside the slab, okay. Here if you apply load also over this particular beam, there won't be any lateral rotation or lateral deflections will be observed, okay. You can't see the lateral deflections in this type of cases. Why? Because we have provided lateral support to this particular flange portion. Because of this lateral support, the beam is not going to deflect, okay. The beam is not going to deflect in lateral direction. We can't see the lateral deflections in this beam, okay. Similarly here, if you provide shear connector, the which we used to connect with the flange portion of the beam section, and this flange portion of the beam section, okay, when you provide when you connect this flange part of this beam section with some steel angle section, which is called as the shear connector, okay. This one is also we used to call as the laterally supported beams, okay. This I beam also called as the laterally supported beam. This particular connection won't allow the lateral deflections in the beam, okay. Similarly in columns also, to overcome this lateral deflection, we used to provide some cross bracings inside the beams, okay, columns. Okay, if it is some of the columns, and for the beams also we used to do same thing. Okay, here you see, here here also we have provided some cross frame type of structure, bracings type of structure. These also provide torsional resistance to the or lateral buckling of the girders beams. You can see here this buckling will be overcome by this action. Okay, and here this buckling will be overcome by this particular bracing member. Okay, by providing solid material also we can provide the lateral support. Okay, these are called as the diaphragms, and here we can provide the lateral support of the beam in this case also. Okay, and after that, after knowing all these things, we can go for the design of the beam. Okay, to overcome this all these deflections and also overcome the moment failures or crippling or buckling failures, we used to take minimum load. We used to find the maximum strength which can be carried by the beams. Okay, how we used to carry, how we used to find those capacity of the beam or bending strength of the beam? As per IS 800 2007, this bending strength of the beams we can calculate, and the design bending strength of a beam can be estimated by using these following steps. Okay, for that one, what we have to do, first of all we have to calculate all the bending moments and shear forces coming from the loads which are applied over the beam. Okay, we have to find the actual bending moment of the section, moment due to the load, and shear force due to the load. Those we have to calculate in case of first step. Okay, in second step, factor bending moment we have to take. We have to factor that particular moment and shear force also. Otherwise we can take the bending moment, factor bending moment, or factor shear force from the step 1 itself. Here what we used to do, factor bending moment we used to find, and factor shear force also we used to find. And now what we have to do, now we have to assume a section, whether you are going to take I section or any other type of section. Okay, if you are going to take I section or any other type of sections. Okay, for that we have to assume one trial section, and we have to check the trial section with final whether a result will be satisfied in moment or not. Okay. This trial section can be selected based on two conditions. One, if you wish to find higher side of the section, you can take this one as this one also as reference. Okay, if you are going to choose any I section, the width of the outstanding leg, if you take outstanding leg for angle section and flange of the sections, okay, that width of those flange section should be more than or equal to the span length by 60. We used to take, these are the minimum span length to span length by 60. If you take this ratio, you can get the width of the flange. Okay, and depth of that particular section or depth of the web of the section we used to take as span length by 45. Okay, the section which satisfied this both the conditions we used to choose as the trial section. Okay, this is one condition. And another condition, as per textbooks they have given, we can take moment by m by I is equal to f by y is equal to e by r relationship. By using this one, we used to find the ZP required using the above equation. First of all, we have to find the plastic sectional modulus of the section of the beams. Okay, plastic sectional modulus of the beam. How we can find this? We can't find directly, but this can be found by using the elastic modulus of the section. By taking maximum moment by applied load, we can know the we will become to know the maximum factor moment of the section m. Okay, that m by f value, if you substitute, this m by f will be gives the ZE value. Okay, m by f will give the ZE value. Okay, and which is nothing but ZE is nothing but I by y. Okay, and from here m by f also we can take. M is nothing but in this case bending moment, which we use, which comes from the applied load. That moment we have to apply it, and stress F we have to apply. Okay, yield stress Fi value we used to apply. Okay, and for that applied load, from here we can get the ZE. And here for I section they have given different type of shape factors for different type of S section. If you want to use I section, then shape factor we used to assume as 1.1. Okay, after taking that 1.1, we have to measure, we have to calculate the ZP required, plastic section required for the beam section. Okay, how we used to calculate? Shape factor into ZE will be gives the plastic section required. And this plastic sections has been given in IS 800 2007 from the table 42 to the 44. For in those tables they have given S value as well as ZP required. Okay. These two values they have given. These two, depending on ZP required values, we used to select the section based on ZP. The selected section should have the more ZP value, okay, then required. Okay, then the section will, then only section will be in safer condition. Okay, in step 4, selecting the type of cross section. Okay, type of cross section. If you are taking I section, that's fine. If you are going to take other sections, there also we can use same thing, same parameters we can take. And selecting the type of cross section which you require for the for I section, whether you are going to take I section or channel section or angle section, that up to you. Up to you. Okay, we have to select the cross section. For that cross section, what we have to do? ZP value of the given section or built up section for rolled steel sections is given in the table, steel table. Okay, the value of the given section or built up section has been given in those sections. We have to select the adequate section depending on ZP value. Okay, and depending on ZP required, we used to select one section, okay, which is having the more ZP value than required value. After knowing this ZP value from the steel table, what we have to do? We have to calculate the, we have to find the whether shear criteria is going to satisfy or not. Okay, for the calculation of the shear capacity VP as per class 8.4 and these classes, using formula we used to use this formula, whereas the shear force shear capacity of the structure VP is equal to Fi TW into dW by root 3. Okay, by taking this one, we can find the shear force which is provided given by the section will be calculated by using this one. Fi TW and dW by under root of 3. This one is given for the equations in 8.4. They have given these conditions. Okay, VP will be calculated, design shear capacity, whereas the VD is equal to VP by gamma m. Design shear capacity will be calculated depending on the VP. VD is equal to VP by gamma m naught. This will give us the shear capacity of the beam section, and this shear capacity has been compared with the design strength of design shear force of the beam section. Okay, this shear capacity VP should be less than or equal to 0.6 VD. Okay, the design bending strength of the section will be calculated by using this formula. They have given these equations in sections 8.2.1.2. They have given this equation. Okay, beta MD is equal to beta B into ZP into Fy by gamma m naught. Okay, if V shear force, this V value, VP value is less than or equal to 0.6 times to the VD, then the design bending strength of the beam will be calculated by using this formula. Whereas beta B will be 1.2 in case of simply supported condition, 1.5 in case of cantilever beam conditions. Okay, for two support conditions 1.2, for single supported beams 1.5, and beta B MD will be beta B into ZP into Fy by gamma m naught. Whereas beta B is equal to 1.0 for plastic and compact sections. For semi-compact sections, we used to take the ratio of ZE by ZP. Okay, by taking these two parameters, we used to decide the beta B value. If you provide the beta B value as 1, the section will be under the plastic and compact section we used to assume. Okay, and these plastic sections also decided from the table 2 which is given in the earlier. Okay, by taking B by thickness of the flange ratio, we used to decide the type of the class of the section. Okay, beta is equal to 1 for the, if you are going to use plastic sections, then beta will be the 1. Okay, and for the for the compact section also we used to take beta B is equal to 1. For other semi-compact sections, we used to take the ratio of ZE by ZP. Okay, after substituting this value in this equation, we used to find the MD value, whereas ZP has been given in steel table, that one we have to take, and Fy will be yield strength, gamma m naught will be known only. Okay, and this MD value should be less than or equal to 1.2 times to the ZE into Fy by gamma m naught for simply supported condition, 1.5 ZE into Fy by gamma m naught for cantilever beam conditions. Okay, and whereas the ZE and ZP are the elastic and plastic section modulus of the cross section. Okay, and these are the other parameters which we used to use in the design to know the bending strength of the beam. Okay, if in case shear force, shear capacity, what we have found in this case VP is greater than 0.6 times to the VD, and the design bending strength of the beam section will be calculated by using this formula. For plastic or compact sections, we used to use MdV is equal to MD minus beta into MD minus MFD. Okay, this value should be less than or equal to 1.2 times to the ZE into Fy by gamma m naught. They have given this one in the IS 800 section 8. Okay, there we can see this formula. Whereas MD is the plastic design moment of the whole section. Disregarding higher shear force effect but considering the web buckling of effect. Okay, MFD plastic design strength of the area of the cross section executing the shear area considering partial safety factor gamma m naught. Beta is equal to 2 into V by VD minus 1. VD we have found that value, VD design here VD will be known in this case. This VD we have to use. This VD we have to use. Okay, if applied force, shear force, VD is V is greater than 0.6 times to the VD. Okay, and we used to design bending strength of the section we used to take. For plastic or compact section, we used to take this one, and any other type of sections we used to use this one. MFD is nothing but here beta B here we used to take as ZFD into Fy by gamma m naught. Okay, ZFD is nothing but, we can see here MFD, ZFD will be ZP minus AW into AY, YW. Okay, area plane shear area of the section here we used to consider ZP minus shear area of the section AW into YW. Okay, W indicates the sectional area, cross-sectional area of the web section, and centroidal distance of the web section we have to take. Whereas AW is the area of the web section, H into thickness of the web we used to take, and YW is nothing but H by 4, the centroidal distance from the center of the section. Okay, top portion of the section we used to take. Okay, this one is the design strength, bending strength of the beam in step 8 when the shear force, applied shear force is greater than or equal to 0.6 times to the design strength of the beam. Okay. Okay, next one. But semi-compact sections, we used to find MD value as design strength as ZE into Fy by gamma m for the semi-compact sections. Okay, the trial section is checked for the web buckling if depth by thickness of the web ratio is less than or equal to 67 times to the epsilon for web without stiffener. You can see here, if you are providing any section without stiffeners, okay, then we can use d by thickness of the web ratio should be less than a 67 epsilon. Okay, why we used to check this one? The trial section is checked for web buckling. The section will be safe in web buckling if it is within the range of 67 epsilon. Okay, the web is generally considered to be safe in web buckling, and the shear strength of the web is governed by the plastic shear resistance. Okay, and we used to follow the deflection limits as per IS 800 2007. They have given like this. If you are applying live load or wind load, okay, on the purlin type of or grit type of member, flexural member, if you take, you can take elastic cladding or brittle cladding, any type of material. Then we used to take maximum deflection for elastic cladding as span by 150 and for brittle cladding as span by 180. That is also assumption which you can make for this deflection check. For live load, which is simple span, elastic cladding we used to take and brittle cladding we used to take. For these two conditions, span by 240 and span by 300 we used to take. For different type of loads, they have given different type of deflection limits as per IS 800 2007 and table 6. If you go there you can see the different deflection limits of the section. The maximum deflection should not be more than these values, span by 150 or span by 180. The maximum deflection should not be more than this one. How we can check these deflections? For suppose if you take any simply supported beam with UDL, then maximum deflection will be 5WL to the power of 4 by 384 EA. If you take point load which is concentrated at the center of the beam, then maximum deflection of the beam will be WL cube by 48 EI. This will be the maximum deflection of the beam, and this deflection should not be more than this deflection limits. Okay, the deflection which is coming from the load, it should not be more than the deflection which is obtained, maximum deflection which is allowed in the beam section, selected trial section. Okay, when it is less than this, if this deflection is less than the maximum deflection limit, then the section is safer in the deflections. Okay, with this I am stopping regarding the introduction part of these beams, and I have followed these two books as reference: Limit State Design of Steel Structures by S.K. Duggal, as well as I have taken IS 800 2007 for the general constructions in steel for the code of practice. Okay, with this I am stopping my lecture for the introduction parts of the beams. In the next lecture we will see the how to solve the beams when it is supported or unsupported beam. Okay, regarding supported and unsupported beams, the designs we will see in the next class. With this I am stopping the lecture here. Okay, thank you.